It's just this that certain CCs are breaking on the M or per and also what I want to do is go through definitions. So what is a sequence? So sequence is a list of numbers which can be finite or infinite. So finite is it comes to an end, or infinite that it goes on forever. Usually expressed in a pattern. No, but not all the time, yeah? That can be expressed or described algebraically. So obviously for this course it's normally described algebraically or in words. So when it's defined algebraically, it is defined in two ways. So defined algebraically in two ways. So the first way is defined by the term number. So this is normally called the nth term. And we say, so said to be deductively defined. The second way is defined from one term to the other. So one term to the next. So this is called a recurrence relation. And this is said to be so either inductively or recursively. Recursively defined. Okay, so let's look at notation. So obviously we're going to be defining in two different ways. So let's look at notation so you see how we annotate sequences. So the first thing is obviously UN. UN is basically the nth term of a sequence. So U sub n. So if we have the sequence, e.g., if we have the sequence 3, 7, 10, it doesn't matter if there's a rule or not, so on, then U1 will be the first term, which is 3. And U4 will be, for example, the fourth term, 1, 2, 3, 4, which is 15. Okay, so U sub n denotes the nth term of a sequence. Now, there's two ways, obviously. So I'm defining it via the nth term rule. So nth term rule is if you have, for example, un is equal to 5n squared take away 6. So if you want to find this sequence, all you have to do is substitute 1, 2, 3, so on into this expression 5n squared take away 6. So when you substitute n equals 1, you get 5 times 1 squared, which is 5 take away 6. So it's minus 1. So gives the sequence. So when we substitute 1 in, we said minus 1. When we substitute 2 in, you get 5 times 2 squared, which is 20. 20 take away 16 is 14. Then if we want to find a third term, we substitute 3 in, 5 times 3 squared, which is 5 times 9, 45, take away 6 is 39, so on. So we can generate a sequence using the nth term rule. Now, recurrence relation. Okay, so for a recurrence relation, we might have an expression. So we might have un is equal to 3 times un take away 1, where u1 is equal to 2. That means, so that implies u1 is equal to 2. Oops, let's just undo. So this gives a sequence. Because we've already defined that u1 is equal to 2, that means we can write, first term is 2. To get the next term, we have to do, to get un, you take 3 times the previous term. So 3 times 2 will give us the next term, which is 6. And then 3 times 6 will give us the next term, 18, and so on. So this one is to get next term is 3 times previous next term, 3 times the previous term. Okay, and so the thing to note is note need initial term or terms for a recurrence relation, because obviously we were using one term to find the next term. We always need to define what the first term or the first few terms are. Okay, let's go through some examples of generating sequences using formula. So the first ones are the nth term, although it looks slightly different. These are the nth term ones, because you can see there is no u. The first term not been given. These are the recurrence relations. Okay, so let's go through one. So AK is equal to 2 times K plus 1. So that means A1, I have to substitute 1 in. 2 times 1 plus 1 is 3. Okay, next one, 2 times 2 plus 1 is 5. 2 times 3 plus 1 is 7. 2 times 4 plus 1 is 9. And 2 times 5 plus 1 is 11. We only need the first 5 terms, so stop when you've got the first 5 terms. 2 is 3k plus 2 to the power of k. So first one will be 3 to the power of 3 times 1 plus 2 to the power of 1, which is 3 plus 2, which is 5. Second one will be 3 times 2. Maybe I should show my working out. 3 times 2 is 6. 2 squared is 4. 6 plus 4. Next one will be 3 times 3, which is 9, plus 2 to the power of 3, which is 8. Next one will be 3 times 4, which is 12, plus 2 to the power of 4, which is 16. And the last one that I need will be 3 times 5, which is 15, plus 2 to the power of 5, which is 32. So when I write this out, when I work it out, I get 5 for the first term, 6 plus 4 is 10, 9 plus 8 is 17, 12 plus 16 is 28, 15 plus 32 is 47. So that would be my sequence. 3, a to the power of k, a sub k is equal to 1 over k. So first substitute 1 in. 1 over 1 is 1. 1 over 2 is a half. 1 over 3 is 1 over 3. 1 over 4, 1 over 5, so on. That one was pretty easy. Question 4. First one will be 5 plus minus 1 to the power of 1, which is equal to 5 minus 1, which is 4. Next one, minus 1 squared, will be obviously 1. So that means 5 plus 1 will give you 6. Now what you realize is every odd number will give you 4 and every even number will give you 6, because minus 1 to the power of an odd number is minus 1 to the power of an odd is equal to minus 1, and minus 1 to the power of even is equal to 1. So you end up getting this periodic sequence, so on. I just needed to do up to the 5th term. So that is it. 4, 6, 4, 6, 4. Okay, next one is 5. So these are the recurrence relations. So A1 is 12. They always give you the first term at least. So next one, to get the next term, I have to take the previous term and add 3. So 12 is the previous term, add 3 gives you 15. To get the next term, I take the previous term, which is 15, add 3, 18. 18 add 3 is 21. 21 add 3 is 24. Okay, first term is 72. It's been defined for you. Minus 0.5 times 72 gives you minus 36. Minus 36 times minus 0.5 gives you 18. 18 times minus 0.5 is minus 9. Minus 9 times 0.5 is 4.5. Okay, question 7. A1 is 1. Okay, so you take the previous term. I might have to do a bit of working out because this one looks a bit complicated. So this second term will be 1 plus 2 times 1, which is 2, plus 1. Next term will be, which is 4, so it's 1, 4. I'll do the working out underneath it. So the previous term is, for the next term, previous term is 4 plus 2 times 3, which is 2 times, did I do it right? The first term was 1. To get the second term, I do A1 plus 2 times 1 plus 1. Next one will be A2 plus 2 times 2, which is 4, plus 1, which is 9. The next term, I'm going to get 9 plus 2 times 3, which is 6, plus the 1, which is 16. Looks at the square numbers. Last one I need to do is 16 plus 2 times 4, which is 8, plus the 1, which is equal to 25. So I do end up getting the square numbers. 16 plus 8 plus 1. Okay, question 8. Okay, so A1 is 0, A2 is 1. To get the next one, you add the two previous ones together. So 0 plus 1 gives you 1. 1 plus 1 gives you 2. 2 plus 1 gives you 3, so on. Okay. Write deductively and recursive definitions if possible that will generate the following sequences. So let's look at A, B, and C. A is equal to 7, 10, 13, and 16. So the nth term, because we're adding on 3 each time, I know the nth term, which is equal to un. No, sorry, let me just write. So deductively means the nth term formula. So I know that means un will be equal to, because we're adding on 3 each time, it must be 3n. 3 times 1 is 3, so I need to add 4 to get 7 for the first term. So un is equal to 3n plus 4. So that's, I've written a deductive definition. Now I need to write a recurrence relation for this same thing. So for a recurrence relation, I need to first define what the first term is, which is u1 is equal to 7. To get the next term, which is equal to un, I need to take the previous term, so un minus 1, and add 3. Now this is the same thing, just to be aware, same as writing u sub n plus 1 is equal to un plus 3, because that still means to find the next term, you have to take the previous term and add 3, and u1 is equal to 7. So it doesn't matter as long as this and this are 1 away from each other. Okay, let's go to B here. So B is 15, 45, 135, and 405. What you notice is you're timesing by 3 each time. So that means if I'm looking at my nth term, so my nth term formula. So what I realize is to find my first term, I got 15. For each one I'm timesing by 3, so it's times by 3. But for the first one, I didn't time by 3, so I need to do 3 to the power of n minus 1. Because then if I substitute 1 in, I get 1 take away 1, which is 0. 3 to the power of 0 is 1, so 15 times 1 is 15. So I do end up getting the right thing. Okay, to get a recurrence relation formula, I need to first obviously write down what the first term would be. My first term, u1 is equal to 15. To get un plus 1, I need to do 3 times the previous term. So that would be it. C is 1 minus 2, 4 minus 18, 16, so on. What I realize is I'm timesing by minus 2 each time. So my nth term formula, which is deductive definition, un is equal to, what I realize is they're all minus 2 to the power of something. But obviously for the first one, I need to do minus 2 to the power of 0, which means I have to do n take away 1, because 1 take away 1 will give me 0. Okay, and if I want to write a recurrence relation, then u1 is equal to 1 and un plus 1 is equal to minus 2 times un, because you take the previous term and multiply it by minus 2. Now, what you should have realized is it's easier to write a recurrence relation sometimes than an nth term formula. Okay, so what I want to do in the last bit is go through types of sequences. So types of sequences are, a sequence can be convergent, and what that means is it goes towards a finite value. Tends towards a finite value. And a sequence is divergent if it does not tend to a finite value. Okay, so let's go through all the different things you can have. So a sequence can be convergent and increasing. Okay, convergent and increasing means, so you might have something like this. So it's increasing slowly, but it's going towards a certain value. So for example, this one, if I look at this sequence, half, 2/3, 3/4, 4/5, 5/6, you can see this sequence is getting closer and closer to 1. So it's tending towards 1, which means it's converging to 1. And it's also increasing, because it's getting closer and closer to 1. It's increasing, but it's not getting to 1. So that is a sequence that's convergent and increasing. Un is equal to n over n plus 1. Okay, decreasing now. So it's the same concept, but the only thing is it starts off obviously at the highest, and then it's going down, and it's getting closer and closer to a certain value. So for example, if we do 1, look at the sequence 1, half, a quarter, 1/8, so on. We can see it's getting closer and closer to 0, so it's tending to 0. So it's a convergent decreasing sequence. Okay, so un would be equal to, for this one, an example would be un is equal to 1/2 to the power of n minus 1. Okay, a periodic sequence cannot be convergent because it does not tend to a finite value, because it goes up and down, and that's it. It doesn't get closer and closer to any value, so that doesn't work. Okay, oscillating. Okay, an oscillating one, as long as the numbers are changing and it's tending towards a certain limit, it can be an oscillating convergent sequence. So if we look at this one, 1 minus a half, this sequence minus a half, quarter, minus 1/8, 1/16, you can see that this sequence is getting closer and closer to 0, but it's also oscillating. It's not increasing or decreasing, so it's oscillating. So the one example would be 1/-2 to the power of n minus 1. Okay, so divergent is when it does not tend to a finite value. So it's increasing one is quite simple. It would be like it's going up, it's increasing, but it doesn't tend towards a certain limit because it's tending to infinity. So an easy one would be un is equal to n. So 1, 2, 3, 4, so on. Similarly, if I want to do a decreasing sequence, it might be something like this. I start off at 0, minus 1, minus 2, minus 3. So un is equal to minus n plus 1 is an example. Even if it's minus n, that would still be an example. Okay, a periodic and divergent means it doesn't tend towards a limit and it's going up and down, obviously. So it might be 1, 0, minus 1, 0, 1, so on. Oh, actually, let's look at a better example that I can give. Because it'd be easier to define 1 minus 1, 1 minus 1, so on. You can see it doesn't tend towards a certain finite value because it's obviously going from 1 to minus 1. And also is periodic because the numbers 1 and minus 1 are repeated. So that would be un is equal to minus 1 to the power of n minus 1. Because if I introduce 0, it would just get a bit more complicated. And one that's oscillating but divergent is obviously one that's, instead of in the convergent one, it's getting closer and closer to 0. For that one is obviously not getting any closer. So something that gets bigger, so on. So that would be, for example, minus 2, 4, minus 8, 16, so on. So un is equal to minus 2 to the power of n. Now, convergent sequence, is it bounded? If you can see, if you can look at it, yes, this is bounded. That one is also bounded. And is bounded. Okay, so all convergent sequences are bounded. None of them are unbounded. Should say none. Okay, divergent. Which ones are bounded? It might be a periodic one is bounded, yeah? So the only one that's bounded is a periodic one, so something that looks like this goes from 1 to minus 1. So it's un is equal to minus 1 to the power of n, for example. Which ones are unbounded? It's anything that's increasing, doesn't have a limit, so something that increases like this. Un is equal to n plus 1 is unbounded. So periodic can be bounded, and the others are not. So increasing, decreasing, oscillating. So these are all the different types of sequences. It's a good thing to have in mind. We'll come back to periodic sequences later on in this topic.